This is the 2015 Queensland Senior External Exam for Physics. We're looking at Paper 1, Part A, Section 2, Short Response, and we're looking at Question 6. First thing we need to do is carefully read the question. A two-point light source interference experiment used to determine the wavelength of monochromatic light source has a screen placed 5.3 metres away. If the slits have a 0.001 millimetre separation and the dark fringes on the screen have a uniform 3.2 centimetre separation, what is the wavelength of the light source? And we've got 3 marks. We've read the question. Now we want to go back through when we want to identify the important pieces of information. A two-point light source interference experiment used to determine the wavelength of monochromatic light source has a screen placed 5 metres away. 5.3 metres away. Let's highlight the 5.3. Continuing to identify. If the slits have a 0.001 millimetre separation, so we need to highlight that, and the dark fringes on the screen have a uniform 3.2 centimetre separation, what is the wavelength of the light source? So the wavelength is what we're after. We've identified the important pieces of information. Now we need to draw. So we need a two-point light source. The way that we set up a two-point light source is we have one monochromatic light source that shines through these 2 slits. So that's our two-point light source, and they go to a screen 5.3 metres away. So here's our screen, and we have a distance of 5.3 metres, like so. Now that's L, the distance away for our screen. If the slits have a 0.001 millimetre separation, so the distances for our slits, D, 0.001 millimetre is our separation, and the dark fringes on the screen have a uniform 3.2. So we'll have a central maximum, and then we'll have our first minima, and then we'll have a central maxima, then we'll have our first maxima, then we'll have our second minima. So central maxima, first maxima on either side, and here we have minima or dark bands, minima, 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 minima. On either side of our central maxima is our first minima, and then the second band is our second minima, like so. And we have here that there's a 3.2 centimetre separation. So these here are 3.2 centimetre separation. That's our delta X value, which is our separation between our bands. So we've drawn. Now we need to try and decide how we're going to solve the problem. So let's go through and now write all this information down. Our slits have a separation of 0.001 millimetre. So I'm going to multiply that by 10 to the minus 3 to make sure that it's in metres. So that's our D value. Our L value is 5.3 metres. And the separation of our slits, delta X, is 3.2 centimetres. So I'm going to multiply that by 10 to the negative 2 to make sure that I've got it in metres. So there we go. We've got all of our information from the question, and we need to know lambda. So we need a formula with lambda, delta X, L, and D in it to solve this particular problem. So now we go to our formula sheet. Here's our formula sheet. We start off here at the top with kinematics, then we go on to light. So this is the light section. Looking through the light section here at our formula, here we go. We have a formula that has delta X, L, lambda, and D. So we need to transpose that formula from our formula sheet and put it down on our answer booklet. Now, this particular formula has delta X as the main feature of it. We actually need to have lambda. So we need to transpose this equation to be lambda equals. So if we multiply both sides by D, we get D delta X on the top, and we divide both sides by L. So we get D delta X on L. Now we need to put our values in. Our D is 0.001 by 10 to the negative 3. we multiply that by our delta x value, 3.2 by 10 to the negative 2, and we divide that by our length. Our length is the distance our screen is away, which is 5.3. Now they're all in metres, so I can now use my calculator to calculate those particular values. So here's my calculator, 0.001 multiplied by 3.2 and divided by 5.3 equals, so that's 0.0006, 0.0006 multiplied by 10 to the negative 3 and 10 to the negative 2 was 10 to the negative 5, and so now 0.6, the further digits on here are 0377358, but I know when I look at my information here, that's two significant figures, that's two significant figures, that's one significant figure. I only need to give my answer to one significant figure. Now, to write that in standard form, I need to move my decimal point 1, 2, 3, 4 places to the right, which is 10 to the negative 4. So 6 by 10 to the negative 4 by 10 to the negative 5, adding our indices is by 10 to the negative 9 metres. So 6 by 10 to the negative 9 metres. So let's go back and have a look at our question, because we need to make sure, after we've done our evaluation, that we can make sure our answer makes sense. So what are we asked to calculate? What is the wavelength of the light source? So for the examiner, the wavelength of the light source is lambda equals 6 by 10 to the negative 9 metres, and it's to one significant figure. Now when we have a look at our answer sheet, we get 1 mark for getting this formula here in the right form. We get 1 mark for substituting the values incorrectly, and then we get 1 mark for our answer. That's the 3 marks that the question is worth.